Okay, well, I guess we'll go ahead and get started tonight. Thank you for joining us for our monthly Ask a Physicist webinar. Tonight's topic is, what is the origin of time's arrow? As the subject of today's event is time, we would like to extend a special welcome today to Robert Brose, whose late wife, Melanie, was fascinated by biology and the nature of time. The Melanie Brose Archelon Fellowship supports the Beyond Center research in this area. In regards to questions tonight, please feel free to use the Q&A option that's at the bottom of your screen, or you can go ahead and use the chat option as well. And without further ado, I'm going to turn it over to the Beyond Center for Fundamental Concepts in Science Deputy Director, Sara Walker, who's going to moderate tonight's event. Sara?
Thanks, Katie. And thanks everyone for being here with us tonight. It's an exciting topic to talk about, and I'm sure many of us have a lot of questions about time, especially given that our perception of time has probably radically changed in the last few months being stuck at home. I feel like time's going a lot slower for me. So it's with great pleasure that I get to introduce my colleague, Paul Davies, who is the director of the Beyond Center for Fundamental Concepts in Science and also Regents Professor at ASU. And he is a world-renowned astrobiologist and cosmologist, but most important for the purposes of today's discussion is he literally wrote the book on the topic that we're going to be hearing about tonight. Paul wrote a book in 1971 on the arrow of time that was so definitive in its treatment of the topic that John Wheeler, who is one of the most famous physicists of the 20th century, had said, at last, a sensible book on the arrow of time. So we're actually going to hear from Paul tonight some sense on the topic, which obviously there's a lot of debate around whether it exists or it doesn't exist and in what capacity. So I'm going to hand over to Paul now, and we look forward to your questions at the end.
Thank you, Sara, for that kind introduction. And we live in this new wonderful Zoom world where we can connect with anybody, anywhere, anytime from our homes. And so that's the good news. The bad news is always that if there's a barking dog outside or some other extraneous noise, we just have to put up with it. So that's a warning. The topic of the arrow of time, as Sara mentioned, well, it goes back into the dawn of history, but my own personal involvement was ever since I did my PhD in London in the late 1960s. So probably the most gloomy pronouncement ever made in the history of science was delivered in 1852 by a Lord Kelvin. And basically, Kelvin said that the entire universe is dying. Can't get much more gloomy than that. And this pronouncement was based on the then new second law of thermodynamics. Now, what is that? Well, if you open the great book of nature, somewhere near the beginning is a statement of this law, perhaps the most fundamental law in all of physics. And won't get too technical at the moment, but basically it says that things are much easier to break than they are to make. It's much easier to disorder something than to order it. Any of our viewers today who have teenage children will know exactly what I mean. And so it is a general tendency among physical systems that they tend to degenerate or become more disordered over time. And there are many, many examples from the world about us. I think this says it all. It's really very easy to disorder an egg. You just have to drop it from the work surface, but it would be very hard to go from what you see there on the screen back to this. To get something like this, the intact egg, you need, well, at the very least a chicken, and probably a lot of food and life support system. And so it's a very complicated thing to get an egg, very easy to destroy an egg. To take a rather more tragic example, but it's still an example, that an earthquake takes a long time to build a building, to put all the bricks in place, but only a few seconds for it to collapse as a result of an earthquake. And we say that this change is irreversible because we never seem to encounter occasions when the earth shakes and all the bricks rise up to form a building. It seems like once the damage is done, it's done for good, an irreversible change. And if we look around in the natural world, there's one very conspicuous example of irreversible change, which is right up there above our head, and that is the sun. The sun is generating energy. It's pouring heat and light into the universe at a prodigious rate. A few years ago, I sat down and figured out in dollar terms how much it's squandering per second, and there you see it. When I say squandering, only about 2 billionths of the sunlight actually hits the Earth, so to speak, does any good. The rest goes off into the depths of space and is wasted. And so this is a classic example of a system where heat is flowing from hot to cold, and you can't get it back again. It's an irreversible degeneration. And of course, as a result of this, the sun will eventually die. Before it does so, it's going to swell up and probably engulf the Earth. But in a few billion years, it'll run out of fuel and shrink and become a white dwarf. And other stars die either that way or in more spectacular ways. And if you go out on a dark night and listen very carefully, the sky is alive with the screams of dying stars. When you add it up over the universe, they're dying at a phenomenal rate. And here's a picture of the death of a star. This is a supernova explosion, and this comes about usually in a star more massive than the sun. And when it happens, the star outshines or almost outshines the entire galaxy. So stars are not forever. They live for maybe some billions of years, but then they succumb. And so these general trends that I've been talking about are what led physicists in the middle of the 19th century to declare that the universe is dying. There was much discussion of the heat death of the universe, that it would basically expend all its sources of energy, run down, and reach a final state which was irreversibly in a state of thermodynamic equilibrium. Couldn't run it backwards again. And it was then perceived that this imprints upon our world this so-called arrow of time. If I have time, I will say a little bit about the confusion caused by this metaphor, but let me just press on. We have this distinction between past and future. We, in daily life, have very little difficulty in understanding that yesterday is different from tomorrow. At the very least, there's not much we can do about yesterday. Those changes are irreversible, but we feel the future is somewhat open. So we can change the future, but we can't change the past. What is the fundamental reason for that asymmetry in the nature of the world, in the nature of time? One way, a very useful way of thinking about this is if you take a movie of an everyday scene and play it backwards, everybody laughs. And the reason that they laugh is because it's so preposterous. We can tell immediately from a movie played backwards, unless it's some static thing, we can tell immediately we've been tricked. And so what is it precisely that is giving us this arrow? Well, in physics, of course, a laugh test is not enough. You have to have some sort of quantity that you can measure. And a long time ago, middle of the 19th century, Ludwig Boltzmann and others who founded the subject of thermodynamics came up with the sort of archetypal archetypal system to analyze this irreversible nature of physical processes. And what you're seeing here is a box of gas divided into by a membrane. On the left, you've got yellow gas, and on the right, you've got blue gas. Now, if you take the membrane out, what happens next, it happens very rapidly because the molecules are moving very fast, is they soon become intermingled. They're jiggling around and they just get mixed up like that. And that's a very good example of the arrow of time. The earlier state is more ordered than the later state. Now, we never enter a situation where we start out with a box of gas like that, and spontaneously, all the yellow molecules retreat to one end and all the blue molecules to the other end. So it looks like the law which governs intermingling of molecules is time asymmetric. There is an arrow of time imprinted on that. But the mystery comes, and it was recognized in the 19th century, when we look at the reason for the mixing. It's intermolecular collisions. The molecules are moving very fast, they bang into each other in a random way and get all muddled up. But if you look at any two molecules colliding, then the laws that govern the motion of those molecules are reversible in time. There's as many going forwards as going backwards on those trajectories. Think of it this way. The Earth is going around the sun in a particular direction. If you look at it from, I'm trying to think, from sort of underneath, so to speak, it's going around clockwise. But it could equally be going around anti-clockwise. That wouldn't violate any laws of physics. So if something can go one way, it can go the other way. And it's easy to see that with individual particles, but when you've got a whole lot of them, then we sort of lose sight of that. And so there seems to be a bit of a paradox going on here, that on the one hand, the laws of physics themselves are symmetric in time. That is, under time reversal, if you just take the equations and put t equal to minus t, the laws don't change. There is one tiny exception to that in the realm of the weak interaction in particle physics, which leads to some obscure, difficult to measure effects that I don't think have any relevance to children's bedrooms. So I'm not going to mention that. But the world clearly around us is asymmetric in time. So how does the asymmetry come out of symmetry? If the world is described by the laws of physics, where does that asymmetry come from? And that's the fundamental paradox. And it was recognized as a paradox way back. So the conclusion is that if we apply the laws of physics to a box of gas, there isn't an arrow of time in the box, so to speak. There is no law-like compulsion for the molecules to go from ordered to disordered. So clearly, the origin of time's arrow has to come from outside the box. And when you think back to when the membrane was sitting in the box there, the box of gas started out in an ordered state. That was the initial conditions. It began ordered and it became disordered. And so you have to ask, how did it get ordered in the first place? That's the correct question. That's where the origin of time's arrow lies. It's with the initial conditions, not in the laws themselves. Very good analogy is with a deck of cards. I am told, I often write this, I've never actually checked, but if you go and buy a deck of cards from your local supermarket, when you open the pack, you'll find that they've been arranged in numerical order and pseudo order. Now, if you shuffle the cards, there's a very high probability that they will be less ordered when you've shuffled them than when you bought them. Now, imagine that you took a deck of shuffled cards, gave it to somebody, they shuffled it again, gave it back to you, and they were in exact pseudo numerical order. Well, what would you conclude? You conclude that you've been tricked. Well, this was a magician or a card sharp, and you wouldn't believe it. But of course, we know on elementary statistics that if you go on shuffling long enough, just by chance, eventually you could get those cards back into pseudo numerical order. Obviously, the probability is exceedingly small, but it's not zero. It's not impossible to shuffle the cards back like that. And the same thing with a box of gas. It's not impossible that if you wait long enough, the molecules would unmix themselves or all rush up to one corner of the box. But the duration you'd have to wait is staggering. It was estimated by Henri Poincaré at the turn of the 20th century to be about 10 to the n years, where n would be the number of molecules in the box, say typically 10 to the 23. So we're talking about 10 to the power 10 to the power 23. And if you're going to ask me, well, what are the units of that? Well, it doesn't much matter, does it, whether it's seconds or millennia, because a few extra powers of 10 don't make much of a dent on that huge number. So in other words, again, there is nothing time asymmetric about the box of gas itself. Wait long enough and it would get back to that initial state. So that's no help to us at all. Well, of course, we don't have that long to wait because the universe is only 13.8 billion years old. It's not been around for anything like this length of time. And so we can only explain time's arrow if it is the case that the universe started out in a more ordered state than it's in now. Well, did it? We now know a lot about the early universe, and in particular, we know this. Now, this is a heat map of the sky made by the European Space Agency's satellite called Planck, and named after Max Planck, of course. And basically, it surveys the whole of the sky and produces this color pattern, this mottled pattern. When you look at that picture, your first thought is, well, it's complicated. But actually, that's missing the point. The key point about it is that to 1 part in about 100,000, the temperature of the universe is the same across the sky. If we look over that way, we get a certain temperature. We look over that way, we get a certain temperature. Seems to be matched to this very high degree of precision, which is to say that the stuff that was coughed out of the Big Bang 13.8 billion years ago was incredibly smoothly distributed, and the heat radiation is incredibly uniform. And when I say coughed out of the Big Bang, 380,000 years is the snapshot that we have here with the Planck satellite. And that sounds like a long time in human terms, but compared to 13.8 billion years of the age of the universe, that is a very, very early epoch indeed. So what we know about the early universe is that it was actually very highly ordered. But now, when we look around us, well, we don't quite look around us. You need a very powerful telescope to get a picture like this. This is the Hubble Deep Field. What we see is a great deal of complexity. And in particular, we see the universe not smoothly distributed, but organized into stars and clusters of stars and galaxies and clusters of galaxies and superclusters of galaxies. So there's a lot of clustering and clumping on pretty much all scales of size, right up to the very largest. And this growth of clumpiness is no surprise. It comes about because of the efforts of gravitation. Gravity has a natural tendency to pull things in. So if you start out, remember that Planck picture, those temperature variations simply track density variations. There are regions of the universe slightly more dense or less dense than the others, and that's why their temperature is slightly different. And the more dense regions draw in material and become even more dense, and the less dense ones lose it, they're denuded of matter, and so we end up with an enhanced density contrast. So gravitation has the effect of taking something smooth and simple and making it clumpy and complex. And that's been going on throughout the history of the universe, and it will go on. The ultimate end state of this clumping together is a black hole. And this is, I think, the only formula, more or less, I'm going to use in this lecture. This is the entropy of a black hole. Now, I haven't actually introduced the word entropy yet. Anybody who knows anything about physics will know that this is a favorite way of measuring the disorder of a system. And I've said the arrow of time is about the growth of disorder, which, if you invent this quantity and define it carefully, called entropy, means that the entropy goes up. So the second law of thermodynamics, which I started out with, is a statement that the entropy of the universe won't go down. It just keeps going up and up and up, and the whole universe is on a one-way slide to a state of maximum entropy or thermodynamic equilibrium. I have to say that was a situation in the middle of the 19th century. Today, the end state of the universe is a much more nuanced picture, and there's all sorts of goodies on offer, like the big rip and the big crunch and the dark energy dominating everything. Won't get into that here. But in 1974, Stephen Hawking came up with this formula because he found that black holes are not actually black. They glow with heat radiation with a characteristic temperature. And alongside this temperature goes a measure of the entropy of the black holes. It is in fact proportional to the area of the surface of the black hole, the event horizon surface. So the entropy of a black hole is a measure, if you like, of its degree of disorder, which seems paradoxical because on the one hand, a black hole looks like it's a perfectly ordered thing, but it also looks like a perfectly disordered thing because it swallows anything that comes its way, doesn't give it back, so it destroys all of the order that existed before. So if you throw an encyclopedia into a black hole, that information is lost forever, although there's some people think it might come back out in trillions of years in some coded way, but won't get into that either. The point being that the black hole represents the final state of gravitational collapse. And when you put the number in for the entropy of a black hole, it's orders of magnitude bigger than the entropy of a star or whatever it might be, or an encyclopedia, whatever it is that goes into that. And that led Roger Penrose many years ago. He was Stephen Hawking's mentor in the 1960s, and it led him to come up with a curious argument because this question about the universe started out very smooth. He wanted to ask the question, well, supposing it started out in some arbitrary state, what would be, what is the probability of a universe, if it just starts at random, being so smooth? And so as a measure of that, he put in the mass of the universe in Hawking's formula. And if you do that, you get an entropy of 10 to the power 123. That's in units of Boltzmann's constant. And then he said, well, what's the actual entropy of the universe? Well, at the time of the Planck heat map, it was about 10 to the power 90. Today it's gone up a bit, 10 to the power, quite a lot, 10 to the power 100, one followed by 100 zeros, but that's feeble compared to the 10 to the power 123, which you get from Hawking's formula. So if you say, well, what might the entropy of the Big Bang have been, the early universe? It could have been anything from 0 to 10 to the power 123. But thermodynamics is this wonderful subject that it relates entropy to probability. You can say, just like shuffling the cards, what are the chances that you will get this or that? But it can give you a precise number, and it's exponential. That is that order is exponentially hard to achieve. And so, and that W map should say Planck, doesn't it? The probability is given by the exponential of the entropy. And so, if we put in the entropy of the universe, put in, like, as it were, the maximum entropy of the universe, 10 to the 123, you see the probability of getting something as low as 10 to the 100. You may think I'm playing fast and loose with the arithmetic here, but I'm not. The probability of getting the universe that we have is 10 to the minus 10 to the 123. And what does all that mean? It means if you have a number 1 followed by 123 zeros, then the odds against getting the universe are sort of 1 in that enormous number. So in other words, we live in a universe which is exceedingly improbable. So that leaves us with the mystery. Okay, we explained the error of time by the fact the universe started out in this very smooth initial state. How did that come about? Not obviously from the creator sticking in a pin, which was the way Roger Penrose liked to explain it. Imagine that you had a sort of smorgasbord of universes on offer. You could have any old initial conditions, and you had a pin and you stuck the pin in. If you stick it in random, the chances are you will get something very disorderly. In order to get the one that is so ordered that we see, the creator's pin would have to be very, very precise indeed. Well, we don't think that's how the universe began, with a creator and a pin, but the primordial smoothness has a natural explanation in cosmology these days with what is called the theory of inflation. All that means is, you've heard of the Big Bang. In the original version, it meant that a split second after the Big Bang, the universe leapt in size by an enormous factor, 10 to the, make it up, but it's got to be at least 60, in a tiny, tiny fraction of a second. So in other words, the universe may have started out in a crinkly, disordered mess, but because of this period of accelerating expansion, everything got sort of stretched out and smoothed out, so that the the state of the universe that emerged from this inflationary phase was highly ordered, highly smooth. So you think, end of story. We've explained the arrow of time. It all began with inflation creating a smooth universe. And some people do stop there, but it does lead to some further problems, because how did inflation happen? This is not a lecture on the inflationary theory. We may do that sometime, but basically it's explained in terms of some sort of field. It's called an inflaton field. Nobody knows what that is. It's just a made-up word for, we've got some ideas, but it's just sort of a made-up solution to a problem. And this inflaton field has to start out in a very, very special state in order to drive inflation. And so you still have to appeal to some initial conditions. You still have to suppose that the universe emerged in some manner we don't understand with this inflaton field in precisely the right state to drive inflation. And people argue about, well, is that more or less likely than the creator of the pin? You know, is this still an exceedingly improbable initial state of affairs? We don't know. These are unresolved questions, and I'm not going to go on much longer. I just want to leave you with the one possible answer to all this is to appeal to a subject called quantum cosmology. That was a subject really invented by John Wheeler. Sara already mentioned him, late and great John Wheeler, but was put on the map by Stephen Hawking and James Hartle in the early 1980s. And what they wanted to do was to come up with a way of describing the whole universe using quantum physics, quantum mechanics. And many physicists think, well, you can't do that. That really is playing fast and loose with the laws of physics. But they did it anyway. And so this leads to the notion in quantum physics, there's this famous Heisenberg's uncertainty principle. A quantum system is indeterministic. There are many possible futures, many possible pathways. And so you can imagine a universe in which there isn't just one branch. We say branches. There isn't just one branch. There are an infinite number of branches, and they all somehow contribute to the wave function of the universe, or the quantum state of the universe. And so it's just symbolically represented by the equation there. And so the plan here is that the whole assemblage of all these possible universes, all these possible branches, is time symmetric. It doesn't have an arrow of time. But within any given branch, there could be a time forwards and a time backwards. They would be equal in number. You'd have as many forward-facing branches as past-facing branches. And depending on your philosophy about the nature of quantum mechanics, you could say these are really real universes. They're all out there somewhere. Some have time going this way and some have time going that way. And of course, anybody living in those universes would always think that theirs had time going the right way and all the others were going backwards. So inevitably, the psychological impression of time's arrow is dictated by the thermodynamics of the world around us. And so that's one way of having your cake and eating it, or having your universe and eating it, or having your arrow and eating it, whatever is your metaphor. But it does mean that ultimately reality respects this time symmetry, but with any given subset of reality, there is going to be a definite distinct arrow. I might say that there's a tiny, tiny subset that I haven't shown here, in which there will be a symmetry within a universe. This would be a universe that where the arrow of time might flip at some stage. I think we've got a question about that coming up, so I'll defer that until then. So I've allocated myself half an hour to speak. You've had your half an hour. I'm going to stop and leave you just with this concluding slide. What is the ultimate origin of time's arrow? It's a mystery. So over to you, Sara, and we'll deal with questions. I'm just going to blank my screen here.
Excellent. Thank you so much, Paul. That was a really great overview. And lots of questions coming in on the Q&A, and then we had a few questions submitted beforehand. So I'm going to start with one for the Q&A. While people are having time to enter their questions, please feel free, and then we'll take some of the ones that came ahead. So for the first question that we had, it was from Matthias Cavendi, and the question reads, what about the case of life on Earth where there is an appearance of increasing order? I think this was in reference to the part where you were saying that the arrow of time follows increasing disorder. And so the question.
Excellent question. We started out with a plug for my first book. We can now have a plug for the last book, which is all on that very subject. It's the nature of life. So that's called The Demon in the Machine. And sure enough, when you look at life, it seems mysterious. It seems to buck the trend of the second law of thermodynamics. It looks like living systems create more order out of order. They don't create disorder. And that's long been remarked upon. It was famously remarked upon by Erwin Schrödinger in his 1944 book, What is Life? And one of the defining characteristics of life is that they will achieve greater and greater order. You have to look at the bigger picture in order to reconcile this with the second law. No living system is isolated from its environment. I showed a box of gas, and implicit in that was that the walls of the box seal off the gas from the outside world. If you seal off an organism from the outside world, it won't live for very long. So living organisms are far from equilibrium thermodynamic systems that export entropy. They generate entropy, they export it into their environment, and there's a throughput of energy and flow of material and so on. And this is what sustains them. But if you look at the bigger picture, you see that the presence of life accelerates the growth of entropy in the universe as a whole. And if we take this sort of gloomy terminology of the heat death of the universe, you might say the part of the price of the biosphere of life on planet Earth is accelerating the death of the universe. So there is that price to be paid. In the 19th century, there was actually quite a lot of thought given to trying to measure these things. So it's been apparent for some time that life is a bit weird, but it all does balance out, and there's no known contradiction with the second law. And I might say, and I won't go on for too long, that in the context of my book, when you look down at the microscopic level, at the nano scale, if you like, the cell's nanotechnology, you find lots of little micro machines, molecular machines, which are playing the margins of the second law of thermodynamics, and they're really right on the edge of what is allowable. And sometimes it seems like they go over the edge, but the book's always balance eventually. And the case that I love to cite is the human brain is full of these little molecular machines, we call them Maxwell demons, and they're so incredibly efficient that the brain has the power of a megawatt supercomputer, but it operates on the energy equivalent of a dim light bulb. And so that shows how thermodynamically efficient living systems are, but they don't violate the second law.
Excellent. So our next question was one submitted before the presentation, which is from Barbara Temple. And the question is, there is an arrow of time, you can only go past from the future, and yet you can travel in space in any direction. According to Einstein's special theory of relativity, space and time are unified. Why isn't there an arrow of space?
Well, that's a very deep question. Time travel is, of course, a subject all unto itself, and I think we won't get into that today. But the asymmetry of time, which is very pronounced, it stands in great contrast to the asymmetry or the symmetry of space. So I took great pains to point out that the Planck satellite gives us a view of the sky in which the universe is the same in every direction. There is no obvious asymmetry. That's not true when we come to our local environment, the Earth, because we recognize that there's a big difference between north and south. I'm actually talking to you now from Australia, which is, as some people may know, in the southern hemisphere. Everything's upside down here. And the point about this is that there's also an arrow that we associate with this asymmetry, this spatial asymmetry of the spinning Earth. It's a compass needle, a compass arrow. And by convention, we say it points north. And that's a very useful metaphor because the asymmetry of the spinning Earth is very much like the asymmetry of time. It's a structural asymmetry of the world in time, just like the spinning Earth is a structural asymmetry of the local region of the universe in space. But of course, the fact that a compass needle points north doesn't mean we are moving north. You don't have to move north to see there's a difference between north and south. In the same way, the metaphor about time's arrow, I said earlier, gets conflated. People often think that the arrow of time is referring to the flow of time. And many distinguished physicists muddle up these metaphors. They talk about the flow of time, when really they mean the asymmetry of the world in time. And I spent a lot of time trying to deconflate these two different uses. It's true we have a psychological impression that time is flowing or moving, but that is a whole separate set of issues that I probably won't mention again today, different from the asymmetry of the physical world in time. Many people think that the flow of time is an illusion or a confusion, but there is no illusion about the fact that the entropy of the universe is going up. That's an objective fact. So we have two different metaphors, arrow metaphors. We've got the arrow as a pointer with an asymmetry, and then we've got the arrow flying through the air, a metaphor of motion. And so don't confuse the metaphor of the asymmetry of time with the motion or the flow of time, or with time travel or any of those things. So I hope that hasn't confused people more than I've explained.
I think that was very illuminating, at least for me. Our next question, I think is maybe in a little bit of a humorous spirit, but is also a very serious question, comes from Phil T. It's a fun question. Why is a black hole black when it isn't black because of Hawking radiation?
Yes. Well, the term, I mean, that's very, very good, Phil. The term black hole was coined by John Wheeler in the 1960s. And what I'm told is that he submitted a paper to Physical Review, the leading physics journal, and the editor said, under no circumstances will we have a paper with the title with the words black hole in it. And I'm old enough to remember when people talked about collapsars and imploded stars and casting around. Wheeler was very good coming up with these sorts of pithy descriptions, and so he introduced the term black hole, and that was in the late 1960s, and it was less than a decade before Stephen Hawking showed that, of course, it wasn't black. It glows with heat radiation, but very feeble. So a solar mass black hole has a temperature of 10 to the minus 8 degrees Kelvin, far, far less than the temperature of outer space from the heat, cosmic background heat radiation. So it's still, pretty nearly black, but of course not totally black. It does glow. At least, if you believe the theory, nobody has ever seen a glowing black hole because their temperature is so low. And to see radiation from a real black hole, you would need to have a very, very tiny one, which would radiate above the background temperature.
Excellent. I just want to encourage our audience again to type questions in the Q&A because we will have a little bit more time to answer more questions.
Don't worry about it. If there are no questions, I can just go on talking.
I still have more. I just want to give opportunity to people to enter more questions as they're having them and remind them that we do have time for more questions. So our next question was submitted ahead, and this one comes from Pat Leonard. The question reads, is it correct to say there is not time separate from space? There is one thing, space-time. And if the answer is yes, then can we say we will continue to move into the future while the universe expands? Time unfolds as long as space grows. And if the universe reaches a limit and then it contracts, will time go in reverse?
Yes, all excellent questions. And questions that I've wrestled with through my career. So let's sort of take them one at a time. The link between space and time was established by Einstein in 1905. So that's something that is absolutely part of physics for many decades. And there's no doubt whatever that you can't separate the two out in any easy way. And so we have to think that we take the two of them together. And the link between the arrow of time and the expansion of the universe is one I could give an entire course of lectures on, because that is very profound, because the one thing I dodged in my lecture, I said the second law of thermodynamics suggests that the universe started out more ordered than it is now. And then I showed the Planck satellite map. What I glossed over is when you look at the spectrum of that radiation from 380,000 years ago, it is precisely a Planck spectrum, named after Max Planck. It's the spectrum of a body or a system in thermodynamic equilibrium. So this looks like a contradiction. Is the universe, early universe, more ordered or less ordered than it is now? And the answer is that gravitationally, it's more ordered. And that was the story I chose to tell. But if you say, well, as far as the matter is concerned, was it more or less ordered? The answer is it was less ordered in the past. It looked like it was a state of thermodynamic equilibrium. Well, how can you go? Didn't I just say the second law says you've got to go from disequilibrium to equilibrium? How do you go backwards? How did the matter of the universe get itself into the present state of being away from equilibrium? And the answer to that is the expansion of the universe. As the universe expanded, it opened up temperature gradients for reasons I won't get into, but they're well understood, and the possibility of this gravitational clumping, which was suppressed in the hot early universe. So the upshot of all this is that the expansion of the universe, in a sense, drives the arrow of time. People always want to say, well, supposing the universe stopped expanding, how long have we got before we reach thermodynamic equilibrium? And the answer is a very long time. And let me now finally deal with this issue about if the universe were to contract, would that make the arrow of time reverse? Would some people say, would time run backwards? But that's an abuse of language. And that's a very curious idea. That's an on-again, off-again idea that's been around my entire career, before my career. So Tommy Gold in the 1960s believed that was indeed the case, that a contracting universe would reverse the arrow of time. I did my PhD thesis on this topic, and I found that it was wrong. There was serious errors of physics. That hadn't stopped other people, and so Stephen Hawking then said, yes, the arrow of time would reverse in a contracting universe, and then he did a U-turn, and he called it his greatest mistake. And this was all very memorable. So he retracted. And then Murray Gell-Mann, a famous Nobel Prize winner, and Jim Hartle, they produced a model in which the arrow of time reverses in a contracting phase. And I wrote a critique of that. And I think the takeaway message from that is that and I mentioned this at the end of my lecture, in principle, you could have a universe in which the arrow of time reverses, but they're very, very rare. You would have to impose final boundary conditions as well as initial boundary conditions. In quantum mechanics, you can do that. You can't in classical mechanics. In quantum mechanics, you get a shot at specifying final boundary conditions as well as initial boundary conditions. So Hartle and Gell-Mann are right in the sense that it is not against the laws of physics. But if you go back to this, what are the chances of this happening? It's going to be very, very small. So that's a rather long answer, I'm afraid, to that cluster of questions, but I hope I did it justice.
No, that was great. So we have a few more questions I'd like to go through. The next one I want to ask, because I also think it's interesting. So this was another one from Mateus. And the question is it not irrelevant debating the probability of a universe that has already occurred? It's quite a deep question.
Yes. So we're here into philosophy, and I might even say theology. And there's a lot of discussion among cosmologists about these sorts of things, because of course naturally they have to worry about such questions. Cosmologists divide into two types. There are those who say, well, look, we've got this universe, we just get on with the job of trying to explain it. And then you've got those like me, well, I think probably Sara would be in this category of thinking, well, you know, there's some profound things here. And so then the question is this the only universe, or might there be many, as I suggested earlier, that if there's an ensemble of universes, then of course mathematically it does make sense to apply statistical reasoning. You can say what are the chances of this one or that one. People have tried to do this. I have to say that when they tried that, but they look at the laws of physics themselves, which also seem to be a bit contrived and a bit weird. And they try to work out, well, what is the probability? And the difficulty is, to get technical for a second, you can't put a metric on the space of initial conditions or the space of laws of physics. People have tried, they've suggested various things. For example, string theory, in principle, would enable you to work out what are the chances in the string landscape of getting just this universe. Calculations are really beyond the scope of our ability or the theory. And so there's a very deep problem about post hoc reasoning. You know, this is what we've got, can we infer about the past? A posteriori or retroactive reasoning. Philosophers squabble over whether this is legitimate and when it's legitimate. But you know, we do it all the time. We see something around us and we think, well, how did that come about? What can we infer about the past? And we make statistical reasoning as we might, for example, at the scene of a crime. Was this natural causes or who done it? And we make this type of retroactive reasoning using something called Bayes' rule. But I'm not going to get into that here.
Excellent. So I'm going to read a related question, which is about the notion of probabilities, but brings in a little bit more of the observer dependence. And this one comes in from Robert Brose. And the question is, although our current universe conditions may seem highly improbable to us, wouldn't the condition in any different path universe seem equally improbable to the observers within them? Or is there a different set of universe conditions far more statistically probable than the basket of conditions we find ourselves in?
So that's the question we would really like to answer. Now, it's certainly true that if you pick any universe, you could say, well, that's a special universe. It's special in its own way. Just like you take the deck of cards I mentioned, you shuffle them, you have some particular sequence, and that's a special sequence, but it sort of doesn't seem any big deal. The ordered suit and numerical arrangement, you think that is special in some way, but you know, why is it special? So you bring in some extra criterion, and the criterion people bring in about the specialness of the universe we happen to be living in is it's the universe we are living in. That is, it's the universe that permits the emergence of living organisms. And when you look at the set of all possible universes, you find that only a tiny subset would be consistent with the existence of life. And so then the question is our existence in such a bio-friendly universe just a lucky fluke? Well, clearly not, because we couldn't live in a bio-hostile universe. So a universe that was sterile, had no life, we wouldn't be here to observe it. So if you associate the existence of observers with the existence of the emergence of life, then you seem to have a selection effect. So not all universes are equal. Some permit observers like us to emerge and ask these sorts of questions. But also in the question that was asked is whether there might be a sort of favored subset. And I think a lot of physicists would prefer if that were the case. They would like to say, we've got all these different universes sort of on offer and somehow could come out of a Big Bang. But if we understood the theory well enough, we would see that the ones that actually make it, maybe the ones that endure or something, would belong to this tiny subset. And just by a happy coincidence, they are the ones in which life arises. That is, most of my colleagues don't like the idea of what's called anthropic selection. They don't like the idea that our existence is the thing that explains this subset. They would prefer that there was in the measure or the space of initial conditions or whatever, that there would be this sort of narrow subset. But nobody's demonstrated this. So that's a job for any young people who are watching us now and are all fired up about this subject. Go away and try and show why the universe had to be more or less like it is.
Excellent. All right. In that spirit, I'm going to go to our next question. This one is from Rachel Phillips. And the question is, as for these universes whose time could run in the opposite direction, what exactly would look different in them? What would distinguish them as opposite from ours?
That's a wonderful question. And I read a science fiction novel once in which there was some mysterious things going on. And it turned out that there was an interpenetrating anti-world in which the arrow of time was reversed. It was sort of slipping across from the anti-world into this one and would grow younger with time, and all sorts of other funny things went on. So this has been thought about a lot. I've mentioned this word entropy, and that I've sort of hinted that entropy is a bit like the opposite of information. I said that if you throw an encyclopedia into a black hole, the information is destroyed and the entropy goes up. And so in a very formal sense, losing information means gaining entropy and vice versa. So if the arrow of time is reversed, in our universe, the entropy goes up. In this other universe, information would go up. So this would look very odd if we could couple into it. But not only would it look odd, you can demonstrate mathematically. Norbert Wiener, the inventor of cybernetics, showed this back in the 50s. If you couple a little bit of the universe with a reversed arrow of time, it's what we would now call a chaotic system. So it's unstable, and it will very soon mean that the dominant arrow of time would come to impose itself on the reversed one. And this very topic was actually part of a lively lecture that I saw Carlo Rovelli give on Saturday night, in which he addressed the question of what happens at the end of a black hole when it evaporates. You can invent something called a white hole, which is a black hole in reverse, time reverse, and you think, well, are there white holes? And the answer is no. If you try and put a white hole in our universe with the reversed arrow of time, it very soon turns into a black hole. Our universe, with its dominant arrow of time, would turn the white hole into a black hole. So he had the idea that maybe the end state of a black hole is some sort of quantum superposition of a black hole and a white hole. I won't go any further down that, but very interesting question. Thank you.
Excellent. Our next question comes from Michael Tovar, who asks, is quantum cosmology another name for a gut, grand unified theory, or is it its own theory / science?
Yeah, thank you for that question, because it goes well beyond what people normally express as a grand unified theory. Let me just back up a bit. There are 4 fundamental forces of nature: gravitation, electromagnetism, and 2 nuclear forces called weak and strong. But in the 1960s, the weak nuclear force and the electromagnetic force were unified into a sort of common mathematical scheme. And then the hope is that the next one will be the strong nuclear force will be amalgamated with the electro-weak force, and then we would go on eventually to include gravitation. That's work in progress. The quantum cosmology, if you had a super duper, ultimately totally unified physics, then it would have to include something like quantum cosmology. But the idea there is, if the universe really is quantum mechanical thoroughly, not just at the level of atoms and molecules, but everything, then you ought to be able to apply it to the universe as a whole. And even if you might think, well, quantum effects are very small, how could the universe possibly manifest anything like that? The answer is, well, once the universe was very small, back in the Big Bang, it was quantum dimensions. It was smaller than an atom. And so quantum effects could have been very important in that early phase, and they may have left a ghost or an echo in the universe around us today. So what's emerged from that, the quantum ferment, if you like, of the Big Bang, and it may be part of the explanation of the origin of the universe, that quantum phase, what's emerged from that is what we would call a classical space-time, in which matter, space and time and matter on a macroscopic scale don't betray any of these quantum effects. But it turns out that in quantum cosmology, you can't just write down any old wave function of the universe and expect to have an emergent classical space-time. It's only a very, very special type of quantum state of the universe that gives us a world of the sort that we have now. So maybe that's another anthropic example of an anthropic selection, and that's certainly what Jim Hartle thinks.
Excellent. So we have about 5 minutes left, which I think means we have time for one more question, which I'll read in just a moment. But before we get to our last question for this evening, I just want to remind people that we have this event once per month. And our next upcoming Ask a Physicist is on the topic of whether or not ET is lurking in our cosmic backyard. So we're going to be talking about aliens and whether they're likely or not nearby or elsewhere in the universe. That's on October 26th, also at 6 p.m., and you can register at beyondasu.edu. So please join us again. And so we have a little bit more time to ask Paul another question. So I'm going to read another question coming in. It's a great question. Let's suppose there weren't an arrow of time. Time would play forward or in reverse. Would we know the difference? After all, our thoughts and memories would wind backwards whenever the rest of time does.
Well, thank you, Barbara, for that additional question. It's when you think about our sensations, certainly when it comes to memories, there is inevitably some thermodynamic asymmetry there. So why do I remember yesterday, I don't remember tomorrow? When you think about the way memories are laid down in the brain, if a memory doesn't last more than a microsecond, then it's not really a memory. There has to be some sort of irreversible fixing of that information in the brain. The brain's a complicated thing, but let's think of the moon. The moon is pockmarked with the effects of asteroid and comet impacts over billions of years. And the early moon would have been smooth. And so over time, these impacts accumulated. And they're like memories of past events. And they don't last totally forever because newer impacts obliterate the traces of older ones. But they sort of built up, and we can infer the past because those memories are locked in. We say they're metastable or quasi-stable. And that's true of human experience. And there are people, at least it's a handful of people, who have a terrible brain condition in which their long-term memory is intact, but their short-term memory becomes compromised, and they can remember only 10, 15 minutes or something. So they'll recognize other people, but they won't remember that they saw these other people half an hour earlier. It's a rather terrible thing. And so I don't think in a universe in which there's no thermodynamics, if you like, in which things are just settled into either a state of thermodynamic equilibrium or some sort of frozen state at zero temperature, that you could have any experiences with anything like we understand by the actual human brain and the way it functions. Of course, we don't understand consciousness, and so we really have no idea whether there could be some sort of disembodied observer that would have those experiences. But certainly when it comes to brains, I think you're pretty, you would be stuck without knowing, without any experiences at all, in fact. So I think we're probably out of time.
We sure are. But that was great. You handled all those questions, amazing answers. So I want to thank our audience again for listening in, and thanks so much, Paul, for all the time answering the questions and the wonderful presentation. And we hope all of you will return next month and bring your questions about aliens. We'll see you then.
Okay. Goodbye, everybody.
Bye.